Thank you for joining this lesson. We're going to discuss physics paper 2, Kcse 2017, number 19. The question says, figure 10 shows a block diagram of a cathode ray oscilloscope, the CRO. Then we have the diagram here. State the names of the parts labeled B1 and B2. So B1 is what we call the wire plates. Wire plates are responsible of what we call vertical deflection, so they can be called vertical plates. The vertical plates. Then B2 are the X plates. So B2 are the X plates, which are responsible of the horizontal deflection and hence can be called the horizontal plates. Horizontal plates. So those are the names respectively, B1 and this is B2. So that is the names. Then we have a part 2 here. State and explain the function of the part marked A. Part marked A is the grid, so it's good we first name it. That is the grid. This one controls the brightness. This controls the brightness at the screen. The brightness at the screen. In other words, we can go ahead and explain how this brightness is controlled, or rather the intensity of the cathode rays controls the intensity of the cathode rays which are reaching the screen. So when the grid is made more positive, when made more positive, remember, electrons are negative, so there will be much attraction. So we say more electrons are attracted, and hence more brightness, hence more brightness. So the more positive it is made, the more electrons will get attracted and hence a greater brightness at the screen. When made more negative, it should be noted that there will be a lot of repulsion because electrons produced at the cathode are also negative. Therefore, there will be less attraction and hence less brightness. Therefore, it is the grid that controls the brightness at the screen. When made more positive, there is greater brightness. When made more negative, due to repulsion, there will be less brightness because less electrons will be attracted and hence lead to brightness. Let us look at another figure here, the same question paper, that figure 11 shows a trace of signal observed on the screen of a CRO. The time-based setting is 20 milliseconds per division, or rather per centimeter. 20 milliseconds per centimeter. Therefore, we have it here. It's just been displayed here. Now, what we need to know is that we can determine the frequency of the signal by first of all knowing the periodic time, because per division this signal is taking 20 milliseconds. So if one division, or rather 1 centimeter, there is 20 milliseconds. What about in a complete cycle of this wave? A complete cycle is having 1, 2, 3, 4, 5, 6, 7, 8 divisions. What about 8 centimeters, which are in a complete cycle, to be 20 times 8? This will give us 160 milliseconds. And this time can be converted to SI units by dividing by 1,000. This will be 0.16 seconds when we divide by 1,000. Therefore, it should be noted now again that frequency is the reciprocal of periodic time. What we have calculated here is the periodic time t, the time taken to cover a complete cycle. The time taken to cover a complete cycle. Therefore, frequency is the reciprocal of period t. This is going to be 1 out of 0.16. This is going to be, let me use my calculator, 0.16. I take the reciprocal, 0.16. This is going to be 6.25. Because it is frequency, the SI units are hertz. So that is the frequency of the signal. Finally, we are told to explain why tungsten is used as a target in an X-ray tube. Tungsten is preferred together with another material called molybdenum. But now, because they are talking of tungsten, let us handle tungsten. This is because tungsten has what we call a high melting point. A high melting point. We can write it in full. A high melting point. A high melting point. This enables it to withstand. This enables it to withstand the great heat. The great heat at the anode. So we know very well when the beam of electrons, fast moving electrons, which are having a lot of energy, accelerated towards the anode. Once they reach the anode, a good percentage, that is almost 99.5% of the energy, becomes heat energy, and a very small percentage, approximately 0.5% of the energy, is what becomes X-rays. Therefore, the great heat energy produced at the anode should be withstood, because if a lesser material or a material having a lesser melting point is used, then it would melt due to the high temperatures. So to avoid the melting of the target point, then we use a material with high melting point to withstand the heat, and that is tungsten. Thank you for following. Subscribe and share.